Share the screen. Okay. So you should have your exam score, and I sent a video on the answers. A couple of things I do have to point out. For number 5, then you had to use the polar graph paper that I mentioned. So some of you didn't, so you lost points if you didn't do that. Okay. Number 6, the main thing about number 6 wasn't the graph. Some of you gave me the entire graph, but you didn't give me the area. The whole question was about the area. I don't need to test you again on making a polar graph. That was what 5 was about. So 6, I just needed to see, one loop and then find the area based off of that. Okay, quickly about 7. I accepted 0, anything, but you're supposed to say the pole. Once R is 0, you're supposed to say the pole. And then you should not list 2 ordered pairs because some of you had negative radical 2 over 2, 5 pi over 4. That's technically correct, but it's the same point as this. So that means you should only list one of them. Normally you list the positive one. Okay. So that's about all I need to say about the test. Okay, so we only have one more test and the final exam, and then we're almost done, folks. So I did some of 11.2 last time. I'll finish 11.2 and do 11.3. At the end, I'll give you a quiz on 11.1 material on sequences. Okay, you say, I don't remember too much about it. Don't worry. I mean, again, I call them quizzes. They're really more just like, assignments. I mean, if you don't want to call them quizzes, don't call them quizzes. Just call them an assignment. And you just work them out, right? You can talk about it. You can help each other out. But, very, very low pressure quizzes, in my opinion, when you get down to it. Okay, so I'll finish 11.2, go to 11.3. So we are where? We're over here. So again, we're sort of pushing this over here. Trying to gain a day just so I can move the exam up to here. Again, a quick reminder, I believe I sent you this in the Canvas announcements a few hours ago, but I'm one of the instructors being evaluated this semester, and so you should have gotten some announcement to evaluate me if you wish. Okay, and so you can put whatever you want. It's anonymous. I don't even get to look at it until next semester, so don't feel like, oh, if I say such and such about him, then he's going to think of me worse or whatever. No, I don't get to see it anyway, and I wouldn't do that anyway. Of course, that's easy for me to say, but yeah, just to safeguard against that, I don't get to see what you all say about me until next semester anyway, after I've already turned in the grades, so it cannot affect your grade. And it's supposed to be anonymous anyway, so I don't know who you are. But yeah, so you're encouraged to evaluate me if you wish. It's not open till the rest of the semester. I think it's only open for a couple of weeks or whatever. So if you want to, technically it's optional. You don't have to do it. I mean, there's no way to tell whether somebody did it anyway. So you can make your comments about me or not. That's up to you. Okay. All right, so we'll continue on with 11.2, which is on series. Just to let you know, everything else in this chapter is on series for the most part, which means you're adding stuff up. Only 11.1 was on sequences. Okay. All right, so let's pick up where we were. And so last time we were starting out on series. And rehash what we had. So for series, page 707, we're adding up the terms. So notation you want to get used to, the sigma notation, n equals 1 to infinity of a sub n, or a sub n is the general term. And after a while, we don't even put the n or the infinity. We know, okay, n is, we could start at 1. We don't have to start at 1. We could start at 2. We could start at 0. And in general, we're going to infinity. Most of the series we're doing are infinite series we're talking about now. Okay. All right, so on page 708, okay, so a series, S sub n is the nth partial sum. Okay, so S sub n means the sum of the first n terms. So S1 is the sum of the first 1 terms. It's just the first term. S2 means this. Sn means this. add up the first n terms, a1 plus a2 plus a3, and so on. So you can say we have a sequence of partial sums, right? So a series can be thought of as a sequence of partial sums. If we approach a number, we say that the series is convergent. If we don't approach a number, we say the series is divergent. Divergent. I will abbreviate convergence if we know that's what we're talking about with C, and divergence with D. In the back of the book does that also. Okay. All right, then other key things for a geometric series. Geometric series. Okay, this is the formula. You don't really have to worry about it that much. Just the idea of a geometric series. After the first term, you keep multiplying by the same thing. It's convergent if the absolute value of r is less than 1. That's like saying r is between -1 and 1. Here's the infinite sum, a over 1 minus r. If absolute value of r is greater than or equal to 1, the series is divergent. Okay. All right, then other things I introduced to you on page 713. If a series converges, then the limit as n approaches infinity of a sub n equals 0, which makes sense. Okay, so if you know you have a series which converges to something, the terms have to approach 0. The logical contrapositive of that, you don't have to write that down, but contrapositive is always logically equivalent. It means you switch the if and the then and put nots. Okay, so if I change the if and the then and put not, if limit n approaches infinity of a sub n does not approach 0, then not this. That means the series is divergent. Something called the test for divergence. It's in the bottom of 713. Test for divergence. I call it TFD. If limit as n approaches infinity of a sub n does not exist, or the limit as n approaches infinity of a sub n is not equal to 0, this series is divergent. Okay, and I showed you that last time. Test for divergence. Okay, and we'll do some more of that. Okay, 714, something new, but I think it is sort of intuitive. If you have convergent series converges, okay, summation of c a to the n is c summation of a sub n. So if you have a constant times the terms of a series, you can just take the constant outside. Like all of these are multiplied by 2. You know, just take the 2 outside and just sum the rest of it. This also seems reasonable. Summation of a sub n plus b sub n is summation of a sub n plus summation of b sub n. It's sort of like the commutative property. And likewise for subtraction. Summation of a sub n minus b sub n, summation of a sub n minus summation of b sub n. Okay, and we'll use that from time to time. All right. So picking up where I left off last time. So I left you hanging with this question. So here was my abbreviation for the test for divergence. Okay. Yeah, test for divergence. If a sub n does not approach 0, which means it approaches another number, or infinity, or negative infinity, or doesn't approach anything, then the series diverges. Okay, so my abbreviations, SC, series converges. SD, series diverges. Test for divergence is this. If a sub n does not approach 0, the series diverges. Okay, and what the text just went over, if a series converges, a sub n approaches 0. The last thing I lectured on last time was, how about the converse? So what's converse? It means you switch around if and then. If a sub n approaches 0, does the series automatically converge? Okay, and now I'll answer that. The answer is no. Okay. Okay, here's a series. Summation n equals 1 to infinity of 1 over n. That's 1 over 1 plus a half plus a third plus a fourth. That's sometimes called the harmonic series. So you'll hear me talk about the harmonic series a lot from here until the end of the semester. Okay, this series actually diverges. Okay, the terms do approach 0. You can tell, right? 1 over 2, 1/3, 1/4, 1/5. 1 over a million, 1 over a billion. The terms definitely approach 0, and yet we actually say that this series diverges. In fact, it diverges to infinity. And the book goes over a proof of that, or a plausibility argument. I will show it to you. You're not really responsible for it. I won't test you on it, but I am supposed to show it to you. Why does a harmonic series diverge? Okay, so in the text, this is page 713. So you want to get comfortable with the so-called harmonic series. It's the sum of the reciprocals of the positive integers. 1 plus a half plus a third plus a fourth. Okay. So they're showing you the partial sums here. So S2 is 1 plus a half. Here is S4, 1 plus a half plus a third plus a fourth. What do they have? 1 plus a half plus 1/4 plus 1/4. Okay, so they replace 1/3 with 1/4. Now 1/3 is bigger than 1/4. Do you agree? So this is bigger, and this is another half. So we added another half. So it's 1 plus 2 over 2, and this is bigger. S8 looks like this: 1 plus a half, third, fourth, fifth, sixth, seventh, eighth. You notice what they did. That's greater than. Leave that alone. Leave that alone. 1/4 plus 1/4. They changed 1/3 to 1/4. 1/3 is bigger than 1/4. And look at what they did over here. They changed 1/5 to 1/8, 1/6 to 1/8, 1/7 to 1/8, and 1/8 they left it alone. 1/5 is bigger than 1/8. 1/6 is bigger than 1/8. 1/7 is bigger than 1/8, and 1/8 equals 1/8. So this sum is clearly bigger than this one, right? I either left the terms the same or I replaced it with a smaller number. Okay, so what? Same, same, smaller, same, smaller, 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 same. So the bottom sum is definitely smaller. And what's 1/8 plus 1/8 plus 1/8 plus 1/8? That's another half. Okay. Do the same thing with S16. Okay, 1, same, half, same. 1/3 plus 1/4, 1/4 plus 1/4. Okay, 1/3 is bigger than 1/4. Then this is the same as this: 1/5, 1/6, 1/7, 1/8, 1/8, 1/8, 1/8, 1/8. This is bigger. 1/9, 1/10, 1/11, 12, 13, 14, 15, 16. Replace them all with 1 over 16. So these are again smaller. There are 8 of these. 8/16 is a half. Okay. So by continuing this scheme, you can add infinitely many halves. You can get as many halves as you want. And if you can add up all the halves that you wish, okay, that approaches infinity, which means the harmonic series, which stays above them for any partial sums, okay, would also approach infinity. So that's the logic. Because you can add infinitely many halves, okay, the sum approaches infinity. Okay, so the harmonic series diverges. So this is our basic standard example of a series where the terms do approach 0, but the sum diverges. Okay, so getting back to this, this is not an if and only if statement, as we sometimes say. If the series converges, okay, you know you have a convergent series, A sub n, the terms approach 0, but not the other way around. If A sub n approaches 0, does the series converge? It still might, it might not. Okay, so the harmonic series diverges. Okay, so that's the takeaway for this. And if you want to put that in your next formula cheat sheet, you may. All right, multiplying all the terms of a series by a non-zero constant. Of course, it has to be non-zero. If you multiply all the terms by 0, it just wipes everything out. But multiplying by a non-zero constant does not affect its convergence or divergence. Okay, that was sort of what this was about. Okay, if you multiply all the terms by a non-zero constant c, okay, well, if this one converges, then this one converges. If this one diverges, then this one also diverges. So that's what we mean by if you multiply all the terms by a non-zero constant, it doesn't affect convergence or divergence. Okay, something else. A finite number of terms that you throw out or put in won't affect convergence or divergence of a series. Okay, so if you're given a series, if you decide to put in a few extra terms, or we decide to throw out some terms, that will not affect convergence or divergence. Now, in the convergence case, it'll converge to a different number, but it'll still converge, period. Here's an example. 1 over 1001, 1 over 1002, 1 over 1000. You can see it's already pretty small. But believe it or not, this still blows up to infinity. This is the harmonic series throwing out the first 1,000 terms. So if I've thrown out the first 1,000 terms, I won't affect convergence or divergence. So this thing still converges. Okay, now let me show you some other stuff. So question 27, or again, my 27 from the homework, which I see doesn't look like it matches. But anyway, 1/3 plus 1/6 plus 1/9 plus 1/12, and so on. Does it converge or diverge? I can factor out 1/3. If I factor out a third, it's 1 plus a half plus 1/3 plus 1/4. It's 1/3 of the harmonic series. What happens in the harmonic series? It diverges. Therefore, this series diverges also. It cannot be a real number. This blows up. If I stop anywhere, it gets big. 1/3 of big is still big, not as big, but still big. So the series diverges. Okay, number 33, or again, my 33. And it doesn't match your 33, unfortunately, but be that as it may. Does it converge or diverge? So n equals 1 to infinity of the nth root of 2. Well, 2, by the way, if you plug in 1, the first root of 2 is just 2. Square root, cube root, fourth root, and so on. Okay. A sub n approaches 1. Okay. 2 raised to the 1 over a million is practically 1. Okay. That's the test for divergence. A sub n does not approach 0. The series diverges. Okay. So if I take the millionth root of 2, okay, let me just try that on my calculator for fun. Millionth root of 2. I guess I get 10 million, but anyway. 1.00000, something like that. It's very close to 1. Which means, in the long run, way out there in the series, toward infinity, it starts to look like 1 plus 1 plus 1 plus 1 plus 1 plus 1, which approaches infinity. So the series diverges by the test for divergence. Okay. Yeah, it looks like a lot of these problems aren't matching at all, but that's the way it goes, unfortunately. But hopefully you're still learning stuff. Okay, 31 is kind of interesting. Again, my 31. And is there anything like that here? No, there isn't. But we'll see. Summation n equals 1 to infinity, 1 plus 2 to the n over 3 to the n. Okay, the way to do this is to break it into 2 pieces. Okay, break it into 1 over 3 to the n plus 2 to the n divided by 3 to the n, or 2/3 to the n. So this is S. I'm going to call this S1 and S2. Remember when we were doing the integral problems? I said the original was I, and then there's I1, I2, I3, and so on. So likewise, S is the original series, and if I have to talk about another series within the same problem, S1, S2. Okay, let's work out S1. Okay, let's write some of the terms out. 1/3 plus 1/9 plus 1/27. Okay, that's a geometric series with a common ratio of 1/3. Is that between -1 and 1? Yes, it is. So the series converges. The formula is A over 1 minus R, or you can say A1 over 1 minus R. So the first term is 1/3 over 1 minus the common ratio, which is also 1/3. 1/3 divided by 2/3, 1/2. In the shortcut, you can just cross out the 3's. Okay, what about S2? 2/3 to the n. Okay, so the common ratio is 2/3. A is 2/3. That converges, right? It's going to be 2/3 to the 1, 2/3 squared, 2/3 cubed, 2/3 to the 4th. So you keep multiplying by 2/3. Okay, so S2 is, by formula, A over 1 minus R. 2/3 divided by 1 minus 2/3. 2/3 divided by 1/3, 2. All right, so the original series S is now S1 plus S2, 1/2 plus 2, 2.5. Okay, then a much more complicated one, 41, and I notice 41 does match, believe it or not. So we'll do 41. 1 over e to the n plus 1 over n times n plus 1. Okay. There's a trick to doing this one. This one's not that bad, actually. Okay, break it into 2. S1 plus S2. So 1 over e to the n and 1 over n times n plus 1. Okay, this is 1 over e plus 1 over e squared plus 1 over e cubed. Geometric. You keep multiplying by 1 over e. 1 over 2.7, that's between -1 and 1. That's going to converge. So S1 is A over 1 minus R, 1 over E divided by 1 minus 1 over E. Multiply top and bottom by E, 1 over E minus 1. How do I do S2? Okay. Well, if you look at some of the terms, plug in 1, 1 over 1 times 2. Plug in 2, 1 over 2 times 3. Plug in 3, 1 over 3 times 4. Plug in 4, 1 over 4 times 5. It's certainly not geometric. Okay. The terms decrease. So how do I figure this one out? Okay, so this is kind of an interesting thing. First, I have to break this up using partial fractions. Do you guys remember partial fractions? Nice review for the final exam, anyway. So I need to split this up. So remember partial fractions? 1, and if you want to know what that is, at 0n plus 1. 0n plus 1 is equal to a over n plus b over n plus 1. Remember that? Partial fractions. Multiply this by n plus 1 over n plus 1. Multiply by n over n. So the common denominator is n times n plus 1. an plus a plus b times n. Gather the n's together. Same as before, only before it was x. These are n's now. So a plus b times n plus a over n times n plus 1. And it has to equal 1 over n times n plus 1, which means a plus b equals 0 and a equals 1. Well, a is 1 is done. That means b is -1. So I can write this 1 over n times n plus 1 as 1 over n minus 1 over n plus 1. Okay, so I claim that's the same as that. And that's easy to verify. If you multiply this back out, you would have, what, n plus 1 over n plus 1, n over n. You'd have n plus 1 minus n, which is 1 in the numerator. So it does verify. Okay. Now, the nice thing about this is notice the following. And let's see. I lost it here, so I have to go to the next page, I think. Let me check. Yeah, next page. So for S2, which was, whoops, I'm changing this to this. And now look at what happens for S sub n. It's 1 minus a half plus 1/2 minus a third plus 1/3 minus a fourth plus 1/4 minus a fifth. And notice these in-between guys all cancel out. Okay? So S sub n is just 1 minus 1 over n plus 1. This is sometimes called a telescoping series. Okay, where if you have a telescope, it collapses. Everything collapses except for the first term and the last term here. The 1/2s cancel out, the 1/3s cancel out, the 1/4s cancel out. This is sometimes called a telescoping series. Okay, so the sum of the first n terms is 1 minus 1 over n plus 1. Clever trick. So if I write it like that, okay, you can see that this doesn't cancel with anything, but everything else in between has a companion that cancel out, except for this one. Okay, so now what happens when n approaches infinity of this limit? Well, that goes to 0, so we have 1. Okay, so it's kind of clever. All right, so finally, S was S1 plus S2. Okay, that E thing was 1 over E minus 1, plus this thing came out to be 1. Okay, and you can get a common denominator, E minus 1 over E minus 1. Add these up. Final answer is E over E minus 1. Okay. All right, then let's see. We have some problems which may not match involving how do you change infinite decimals into fractions using series. Okay, you probably may have learned some techniques in your earlier classes, in your algebra class or whatever. We're doing it with series. I want you to know how to do it using series. Okay, so I'm showing you how I expect you to do it. Okay, so yes, you can get the answer another way. I don't want you to do the other way. You got to do it my way. It's not really my way. It's the calculus way, so to speak, with series. Okay, so like how do you change 0.8 and so on into a fraction? Okay, now if they give you the fraction, you know what to do. You just divide it. Okay, like this one I know happens to be 8/9. So how do you get 8/9? Well, that's simple. Just it's arithmetic. Just punch 8 divided by 9 and 0.88888, right? But how do you go the other way? If you start off with an infinite decimal representation, how do you bring it back to a fraction, ratio of integers? Okay. So again, some of these might match, some of these don't. So how do I want you to do these things? Okay, so 52, I guess that does match this one. 0.4646 and so on. I know it's an even one, but it shows me what I want to do. Okay, write it as 0.46 plus 0.0046 plus 0.000046. Right? This gives me these two digits. This gives me these two digits. This gives me these two digits. Okay? So it's a geometric series with a common ratio is 0.01. So I just use the formula. S is the first term, 0.46 over 1 minus R, 1 minus 0.01. So 0.46 over 0.99, move the decimal over 2 spaces, 46 over 99. Okay, so that's what you do. And by the way, if you line this up vertically, you can kind of tell, right? 0.46 is like that, 0.0046 is like that, 0.00046 is like that. Then if you add them, right, you see, oh yeah, 46, 46, 46. That's what you get. And double check. 46 divided by 99. 46 divided by 99. Here we are, 0.464646 and so on. So it's verified. Okay, 10.135, and you guys should know what the bar means. The bar means that's the repeating unit. So it's 10 plus 0.135, 135, and so on. So leave the 10 alone. That's not the repeating part. So I'm going to call it 10 plus S. Then after I finish, I just combine it with the S. So S is 0.135 plus 0.000135 plus dot, dot, dot. So the common ratio is 0.001. To go from here to here, you multiply by 1,000th. Okay, so the sum is A over 1 minus R. So 0.135 is the first term. A is the first term. 1 minus 0.001, which is 0.135 over 0.999. Move this over 3 spaces. Move this over 3 spaces. 135 over 999. Let's reduce it. Both of these are divisible by 9. You guys ever heard of the rule of divisibility by 9? If the sum of the digits is divisible by 9, then the number is divisible by 9. Ever heard of that? So like 1 plus 3 plus 5 is 9. That means this is divisible by 9. 9 plus 9 plus 9 is 27. That's divisible by 9. So you can divide out a 9. I did that. 15 over 111. You can now divide out a 3. Rule of divisibility by 3 if the sum of the digits is divisible by 3. Well, you already know 15 is divisible by 3. But if you go by the rule, 1 plus 5 is 6. That's divisible by 3. 111. 1 plus 1 plus 1 is 3. That means this is divisible by 3. So I divided out the 3. 5 over 37. Okay, now, in the final answer, they say give as the ratio of 2 integers. Okay. In other words, it's just integer divided by an integer. So 10 and 5/37ths, and you know how to do that from arithmetic, 375 over 37. So that's my final answer. Okay. And let's see. I will show you my 55, which unfortunately doesn't match yours, but that's the way it goes. 1.5342. The repeating part is the 42, you know, right? So separate out the part that doesn't repeat, 1.53. We know how to change that to a fraction, 153 over 100, right? So the harder part is the rest of it. So this is 0.0042. The next 42 would be 0.000042, and so on. So I have 1.53 plus s. Trying to figure out this s. And I already know that's 153 over 100. Okay, the common ratio is 0.01. To go from there to there, you multiply by 100th, 0.01. So that sum is going to be the first term, 0.0042, over 1 minus r, 1 minus 0.01. 1 minus 0.01 is 0.99, or 0.9900. Move over 1, 2, 3, 4 spaces. 1, 2, 3, 4 spaces. 42 over 990. Okay, both of these are divisible by 6. So 7 over 1650. So for the final answer is 153 over 100 plus 7 over 1650. That's just arithmetic. I'll let you work on that. Looks like the common denominator will be, I don't know, 16500, but that's just arithmetic. You figure the rest of that out. Okay. And then some problems at the end. Find the values of x for which the series converges. Find the sum of the series for those values of x. Okay, so this time they got some variables in there. And by the way, most of the rest of the series that we're going to do in this chapter, they're going to have variables, okay, x's. So they're saying sometimes it converges, sometimes it diverges. It depends on what the value of x is. Okay, so how do you do that? Okay, so I'm going to show you 57, which matches mine, and 59 also matches. Okay, so that's good. Okay, 57. It goes summation n equals 1 to infinity of -5 to the n, x to the n, which I'm going to write as -5x to the n. Now, I mentioned last time, when you see something like this, you should highly suspect the common ratio is whatever's in parentheses. So when I see this, right, I think to myself, there's a good chance the thing inside the parentheses is the common ratio. But check to make sure. If I plug in 1, -5x to the first power. Plug in 2, -5x squared. Plug in 3, negative 5x cubed. So it is a geometric series where the common ratio is negative 5x. Okay. So does this converge or does it diverge? Well, it will converge if the common ratio is between negative 1 and 1. We know that, right, for geometric series. So when does a geometric series converge? If the common ratio is between negative 1 and 1. So I set this thing to be between negative 1 and 1. Divide by negative 5, negative 5, negative 5. That changes the inequality symbol, you might recall. Right? If you divide by negative, you switch the symbol. So 1/5 greater than x greater than negative 1/5. But quickly change it back to the way that we like it, which is less than, less than. So x between negative 1/5 and 1/5. So the series converges if x is in the interval from negative 1/5 to 1/5, otherwise diverges. So getting back to this, you say, does it converge or does it diverge? Okay. Well, it'll converge if x is between negative 1/5 and 1/5, not counting negative 1/5, not counting 1/5. So let's say this is negative 0.2, this is 0.2. So if x is 0.1, series converges, or negative 0.1, or 0.005, or negative 0.001, the series will converge. Otherwise, the series diverges, the original. Then it says, what does it converge to? I use the formula, a over 1 minus r. Okay, put this on the next cheat sheet. So a means the first term, negative 5x, over 1 minus the common ratio, it's also negative 5x. So 1 minus a negative 5x. So final answer is negative 5x over 1 plus 5x. Okay, so the series converges, this funny thing here. You say, does it converge or diverge? That's a 5 there. Well, it'll converge if x is between negative 1/5 and positive 1/5, not counting the endpoints. And what does it converge to? This thing. Okay. All right, and 59 also matches, I think. Yeah. They write it as x minus 2 to the n over 3 to the n. Well, I'm just going to write it as x minus 2 over 3 to the n. Algebraically, it's the same thing. And notice they start indexing this one at 0. That's okay. By the way, when you plug in 0, what do you get? 1. That's nice. The first term is 1. The common ratio is x minus 2 over 3. Because after you plug in 1, it's to the first power, plug in 2, second power, third power, fourth power. So what do you keep multiplying by? Well, you keep multiplying by x minus 2 over 3. Right? That will converge if that common ratio, x minus 2 over 3, is between negative 1 and 1. Right? Because for a geometric series, the series will converge if r is between negative 1 and 1. It'll diverge otherwise. So I solve negative 1 less than x minus 2 over 3 less than 1. Okay, so multiply everything by 3, multiply that by 3, multiply that by 3, that cancels this out, multiply this by 3. So negative 3 less than x minus 2 less than 3. Add 2, add 2, add 2, x between negative 1 and 5. Okay, so SC, what is SC? Series converges if x is in the open interval from negative 1 to 5. D, what is D? Diverges otherwise. So for instance, 0. If I plug in 0, series converges. If I plug in 4, the series converges. If I plug in 4.9999999, the series converges. But if I plug in 5, the series will not converge. It will diverge. Okay. If I plug in negative 1, the series will diverge. But negative 0.999999, the series will converge, and so on. What does it converge to? A over 1 minus r. The first term was 1 over 1 minus r, 1 minus the common ratio of x minus 2 over 3. Okay, so this is the answer, but that looks funny, so I'll multiply top and bottom by 3. So the top is 3. 3 times 1 is 3, minus 3 cancels out, x minus 2. And this is 3 minus x plus 2, or 3 over 5 minus x. So the answer is 3 over 5 minus x. That's what the series converges to if I pick an x between -1 and 5. Okay. All right, and I am now done with 11.2. Okay, so what time is it? It's not even 8 yet. Okay, I'll introduce 11.3, and then we'll break. Then after that, I'll do some problems in 11.3, and then give you the quiz after that. Okay, so I'm aiming for roughly, a section and a half every day. So if I do a section and a half every day, I should be able to finish, okay. All right, so 11.3. So right now, most of the rest of the chapter, we're finding tests for convergence or divergence. Does a series converge or does it diverge? And we're learning different techniques. Okay, so let me introduce the next part, which is called the integral tests. It says integral tests and estimates of sums. Never mind about the estimate of sums. We're just doing the integral test. Okay. Integral test. Let me give you the idea of the integral test. Page 721. Suppose f is a continuous, positive, and decreasing function. All of these have to be true. Okay. Put them on your next cheat sheet if you want. It's almost always going to be continuous. For the problems in this section, positive, decreasing. So that's theoretically what we're supposed to check. Okay, between 1 and infinity. Okay, let a sub n equal f of n. Okay, this might get kind of confusing, but don't worry, I'll explain it. Okay, the series converges if and only if the improper integral, remember we did improper integrals before? Integral from 1 to infinity is convergent. Okay, in other words, if the improper integral converges, the series converges. If the integral diverges, the series also diverges. Whatever happens to the integral happens to the series also. What you're essentially doing is taking the series and you're looking at it and say, can I integrate that expression? If the answer is yes, maybe the integral test is the way to go. Okay? We say integral from 1 to infinity. If the index starts at 2, you go from 2 to infinity. If it starts at 0, you go 0 to infinity, although technically it doesn't matter. Okay? So you look at the series and you say to yourself, is it possible to integrate this if I change the n to the x? If you can, then maybe you can do the integral test. Okay? In fact, they have that here. It is not necessary to start the series at n equals 1. You could test n equals 4 or whatever. Okay? And the other thing they mentioned is it's not necessary that f be always decreasing. What's important is that f is ultimately decreasing. Okay? That means for large enough x, sooner or later, it will be decreasing from then on out to infinity. Okay, so example of what's happening. Okay, test summation 1 over n squared plus 1 for convergence or divergence. Okay, so if I change it to x, 1 over x squared plus 1, right? Do I know how to integrate this? Yes, that's my inverse tangent. Okay, so let me show you what the concept is. You say, does this series converge or diverge? This is on page 721 again, if you're trying to follow along. Change it to the improper integral. Integral from 1 to infinity of 1. It's the same thing except change n to x. Okay, so n basically is for series, x is for integrals. Yeah, technically it's the same thing. Well, let me hold it up like that. You can focus it better. Okay, integral from 1 to infinity, right? Okay, we know what that's about. Limit, they say t. I used b before. I'll be using b when I do it. But remember, we're doing improper integrals, right? So t goes infinity, integral from 1 to t of 1 over x squared plus 1 dx. So that's a limit as t approaches infinity of inverse tangent of x. Remember, the integral of this is inverse tangent from 1 to t. Limit as t approaches infinity, inverse tangent of t minus pi over 4. Okay. Now, when this thing gets super big, inverse tangent approaches pi over 2. We talked about that before. Pi over 2 minus pi over 4 is pi over 4. Okay, the integral converges. Since the integral converges, the series also converges. Okay? We do have to be careful, though. We cannot say the series converges to pi over 4. In fact, we know that's not true. It's been shown not to be true. So we're just going to say it converges, period. Okay? And a lot of times for the next several sections, we will be left with the conclusion of saying, okay, we know the series converges, and we don't even know what it converges to. We just say it converges, period. But does it converge to pi over 4 or 2 or 7 or 80? We don't know. Okay? We'll just be able to say we know the series converges. And the only conclusion we can make is the series converges, but we're not going to say what it converges to. So this is the idea behind the integral test. We're going to change it to an integral problem. So when you look at this, right, say, can I integrate that if I change it to x? 1 over x squared plus 1. Yeah, I know how to integrate that. Okay, then you'll change it to an improper integral, just like we did before. Okay. If you want to see a proof of it, the book goes over the mini proof on the bottom of 719. Okay. So it's there. You can look at it or not. Okay. They're trying to show you the convergent case here. Okay. So what they're trying to show is if you take the sum of the areas of all those rectangles, it's less than the area under the curve. Okay. So in the convergent case, whoops. Okay. So if you know that the integral converges, the sum of the rectangle's area cannot go to infinity. It's stuck below something which already diverges. Right? And then in the divergent case, you draw a picture like this. You can show that the sum of the series is like so. So this is divergent case. So let's pretend the integral diverges, meaning in this case to infinity. Well, the sum of the areas of the rectangles is bigger, right? You're bigger than something which approaches infinity, then the infinite sum also has to go to infinity. Okay? So that's the idea there. Okay, so this is the integral test. If you want to put this on your cheat sheet, page 721, okay, I can give you my shortcut variety. Second, so if the integral converges, you have to have continuous positive decreasing. I'll give you my abbreviation for that. Okay, if the integral converges, the series converges. If the integral diverges, the series diverges. Let me show you my abbreviation, and then we'll break. Okay, so integral test. So we change the series for the corresponding integral. What does that mean? Just change n to x. N is for series, x is for integrals. Okay, so f is continuous, C-O-N-T. What do you think that means? Positive. What do you think that means? Decreasing. So that saves a lot of verbiage. And you'll have to say this for me on quizzes and tests. So rather than writing out the entire thing, right? Write out the whole, what? Continuous, positive, decreasing. That's a lot of letters there. It's a lot faster to just do this. My abbreviation, continuous, positive, decreasing. Okay, if the integral converges, then the series converges. If the integral diverges, then the series diverges. Okay, in fact, you can even leave off the then is implied. So you might see me later on if I, C, S, C, which means integral converges, series converges. If I, D, S, D, which means if the integral diverges, the series diverges. Okay, and I'll show you how to do some of those after the break. Okay, so let me stop the share and we will break. Let's see what time is it, 8:02-ish. Okay, so let's start up again around 8:15, please. Okay, 8:15, we'll start up again. All right, so we'll break until then. Thank you. Okay, folks, 8:15, so we'll go ahead and start up again. So I'll be doing some problems from 11.3, finish that up, and then I will give you the quiz. So let me start up again and share the screen once more. All right, so the idea behind the integral test is change the series problem into an integral problem, which we've already done before. Okay. We're going to be integrating with infinity, so we know how to do that. If you've forgotten, we'll just kind of review it. Okay, so first example, does summation n equals 1 infinity of 1 over n squared converge or diverge? It's 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared and so on. Okay, so the integral test says look at the integral from 1 to infinity of 1 over x squared. It's basically the same thing, just change n to x. Okay, all right, 1 over x squared is continuous, it's positive, it's decreasing, right? Generally, they look something like that, in other words. Okay, so whatever happens to the integral happens to the series. If this converges, this converges. If this diverges, this diverges. Okay, so you might recall how we did that. Replace it with a limit as b approaches infinity of the integral from 1 to b of x to the minus 2 dx. So limit as b approaches infinity, x to the negative 1 over negative 1 from 1 to b. Take out the negative, write that as 1 over x. Limit as b approaches infinity of 1 over x from 1 to b is limit as b approaches infinity of 1 over b minus 1. Okay, so when b gets big, this approaches 0. So I have negative, negative 1, which is 1. Okay. So since the integral converges, so does the series converge by the integral test. Okay, so that's the kind of language you would give to me on a quiz or homework or the test or whatever. Okay, so again, the concept is look at the original series and ask yourself, do I know how to integrate 1 over x squared? Sure, I can integrate 1 over x squared. Okay, so change it to the integral. If the integral converges, the series converges. If the integral diverges, the series diverges. That's what all this says. Okay, I did the improper integral. We did that several sections back. Came out to be 1. So the integral converges. Okay. Note, we are not saying the series converges to 1. That's not true. It just converges, period. Okay. In fact, I think the book mentions this. It turns out you can prove in further, more advanced classes, that's beyond the scope of our course, but summation of 1 over n squared turns out to be pi squared over 6. Okay, don't ask how they got that, but that's about 1.5, right? Pi is like 3, 3 squared is 9 over 6. So it's kind of close to 1, but it isn't 1. Okay, so all we can say is that it converges, period. Okay, now let's go back to our harmonic series. Okay, I gave you that proof. Maybe you followed it, maybe you didn't, but you should be able to follow this better. Okay, the harmonic series is summation 1 over n. 1 plus a half plus a third plus a fourth and so on. Okay, so can I integrate 1 over x? Sure can, that's my natural log. All right, so I look at the integral from 1 to infinity of 1 over x dx. Okay, when you have infinity, change it to b. Take the limit as b approaches infinity. 1 over x. That's ln absolute value of x as b approaches infinity from 1 to b. Okay, plug in b. Absolute value of b is b because b is a big positive number. Absolute value of 1 is 1, but natural log of 1 is 0. So limit as b approaches infinity of ln b is infinity. The integral blows up. Since the integral diverges, so does the series diverges by the integral test. Okay, so that's another proof that the harmonic series diverges because the corresponding integral diverges. So for over here, y equals 1 over x, you have an infinite amount of area. Okay, for 1 over x squared, I mean, it has the same general shape. You do not have an infinite amount of area. Total area is 1. Interesting enough. Right, so that shows the harmonic series diverges 1 over n. Now I'm going to change it ever so slightly. Now, you know 1 over n is like 1 over n to the first power. How about I make it just a little bit bigger, 1 over n to the 1.001. Does that converge or diverge? Notice my abbreviations. I don't have to write C-O-N-V-E-R-G-E or D-I-V-E-R-G-E, right, C or D. So we look at the corresponding integral. Integral from 1 to infinity of 1 over x to the 1.001 dx, which I can write as x to the negative 1.001 dx, limit as b approaches infinity of integral from 1 to b. So integrate, and here's the key. If I just raise this a little bit bigger than 1, this is going to be a negative exponent, and when I integrate, I'll still have a negative exponent. That's the key thing. X to the negative 0.001 divided by negative 0.001, limit b approaches infinity. Now, dividing by negative 0.001 is the same as multiplying by negative 1,000. And x to the negative 0.001 means 1 over x to the positive 0.001. Okay, so negative 1,000, limit as b approaches infinity, 1 over b to the 0.001 minus 1 raised to anything is 1. Okay, and now when b gets super big, the denominator gets big, this approaches 0. 1 over big is 0. So I have negative 1,000 times negative 1, positive 1,000. The integral converges, therefore the series also converges by the integral test. Okay, that same logic would apply if I put any exponent bigger than 1. If I did 1.001, the logic would still be the same. Okay, just any number bigger than 1, you'll have a convergent case. But if x is equal to 1 or anything smaller, the series will diverge. So in some sense, okay, you're almost, for y equals 1 over x, you're right at the cutting edge of infinity, so to speak. Okay? You have an infinite amount of area here. Okay? If this were x to any exponent ever so slightly bigger than 1, suppose I put 1 point, put a million zeros, and then a 1. So you can imagine the graph is just a little bit below. All of a sudden, the series will converge. So this is just right at the barrier of infinity, so to speak. It's kind of a weird concept. If I just go ever so slightly below with x to any exponent bigger than 1, 1 point, million zeros, and then 1, the series will diverge. Okay, so that leads us to another law. This is called the P-series rule. I know I haven't even done any of the homework assignments yet, but put this on your cheat sheet if you wish. Okay, you should be considered fortunate because, again, if we were meeting face-to-face, I'd make you guys memorize this. Page 722. P-series. P stands for power. 1 over n to the p. Now, we know that n to the 1, that's our harmonic series, that diverges. But if we just have p ever so slightly bigger than 1, 1.00001, that series will converge. So the P series, what's the P series? Summation of 1 over n to the p. It's convergent if p is greater than 1, divergent if p is less than or equal to 1. Okay, it's called a P series. The reason is because of the integral test. Okay, so for instance, summation 1 over n cubed, 1 over 1 cubed, 1 over 2 cubed, so on. This is a P series where p is 3. 3 is bigger than 1. So by this route, the series converges. On the other hand, 1 over n to the 1/3, which is 1 over cube root of 1 plus 1 over cube root of 2 plus 1 over cube root of 3 plus dot, dot, dot. That's divergent because it's a P series with p is 1/3 and 1/3 is less than 1. Okay. The reason for that is the integral test. If you did the integral test, you'll see that this converges. If you did the integral test on this one, you'll see that it diverges. Okay. All right, so that's called the P series test. All right, so I'm going to start some of the problems, but again, I know that yours don't match mine necessarily, but that's okay. We're still learning stuff. Okay, so my number 5, which does not match. Okay, no, that's okay. All right, summation 1 over 2n plus 1 cubed. So look at the corresponding integral. So what do you change it to? Just change n to x, and you do the same integral. Okay, it's continuous, positive, decreasing, right? So I can do it. So limit as b approaches infinity, integral from 1 to b, 2x plus 1 to the negative third dx. All right, so I integrate limit b approaches infinity, 2x plus 1 to the negative 2 divided by negative 2, and then by the chain rule divided by another 2 because of this. Okay, again, if I were differentiating by the chain rule, I'd multiply by 2. Since I'm integrating, I divide by an extra 2. Okay, so take out the negative 1/4. I can pass the negative 1/4 outside the limit. Negative 1/4 limit b approaches infinity, 1 over 2x plus 1 squared from 1 to b. Negative 1/4 limit b approaches infinity. Okay, this is 1 over 2b plus 1 squared minus plug in 1. You have 2 plus 1 is 3. 3 squared is 9, so 1/9. And when b gets super big, this fraction approaches 0. So I have negative 1/4 times negative 1/9, which is positive 1/36. The integral converges. Since the integral converges, so does a series converge by the integral test. So that's what we're saying. Okay, 7. And let's see, it looks like our number 7s do match, so that's nice. Okay, summation n equals 1 to infinity, n over n squared plus 1. So look at the corresponding integral. All you do is just change n to x. That's just the way you do. I guess you could put n over n squared plus 1 dn, but we normally don't do that. So we use n for series and x for integrals. Just change n to x. Okay, that looks like I can do it by substitution. It's a rational function. It's continuous. I'm only plugging in positive. It's positive. It's decreasing. As x gets bigger and bigger, this thing decreases. Okay. So limit as b approaches infinity, x over x squared plus 1. I know the derivative of x squared plus 1 is 2x. So put a 2 here, 1/2 here. So u equals x squared plus 1. du equals 2x dx. When x equals 1, plug in 1, you get 2. X equals b, put a b, b squared plus 1. I know you're not used to putting b squared plus 1, but that's all we can do, so we got to do it. So the integral now has a half out in front. Limit b approaches infinity, integral from 2 to b squared plus 1 of du over u. You can pretend there's a 1 there. 1 over u. So that tells me it's a natural log, right? Excuse me. Okay, so ln, absolute value of u, 1/2, limit b approaches infinity, ln absolute u, 2 to b squared plus 1. Now, b squared plus 1 is positive, drop the bars. Absolute value of 2 is 2, drop the bars. So 1/2 limit b approaches infinity, ln b squared plus 1 minus ln 2. But we already know when b gets big, ln of big is big. So big number minus this puny number is still big. Half of big is still big, so it approaches infinity. All right, so since the integral diverges, then, or therefore, you can just put SD. So ID, integral diverges, series diverges by the integral test. That saves you a lot of writing, right? You don't have to keep writing all this stuff. Okay, and then number 9, it does match. What do you know? A summation of 1 over n to the radical 2. So that looks like my P series rule. Okay, so put this on your next cheat sheet, the P series. It's on page 722. If you have something that looks like 1 over n to the P, You can have any constant on top. It could be 4 over n to the p. Just take it 4 times 1, pass the 4 outside, and remember, multiplying by a non-zero constant will not affect convergence or divergence. Okay, so if p is bigger than 1, the power is bigger than 1, series convergent. If the p is less than or equal to 1, the series is divergent. Okay, so what do we have? Square root of 2. Okay, that's a p series. P is the square root of 2. Square root of 2 is like 1.4. That's bigger than 1. Okay, that means the series converges. Okay, so I didn't put it, but you can put, okay, series converges by p series. I kind of botched that up. Series converges by p series. P series. Okay. 13, does that match? It does not match, but it's similar. Okay. So 1 plus 1/3 plus 1/5 plus 1/7, you have to make that into a root. Your actual 13 is a little bit different, 1/3 plus 1/7. Okay, you can force that into a root, just like what I'm going to show you. Somewhat. Okay, so 1, 3. So I notice this is 2 minus 1, 4 minus 1, 6 minus 1, 8 minus 1. So a sub n is 1 over 2n minus 1. So summation n equals 1 to infinity, 1 over 2n minus 1, do the integral test. Okay, so that's my hit for you for that one. Okay. 15, and 15 does match. Okay, radical n plus 4 over n squared. Determine whether the series is convergent or divergent. And notice in the convergent case, they're not even asking what it converges to. We don't care. We just want to know what converges, period. Okay. So this one we split into 2. Break it up into that and that. So S1, summation of radical n over n squared. S2, 4 over n squared. And like I was saying, the 4 you can take outside as 4 times summation 1 over n squared. Okay, multiplying by a non-zero constant does not affect convergence or divergence. So if this thing converges, so does this. If this thing diverges, so does this. Right? Not to the same number, but it converges. Okay, now this one you can write as 1 over n to the 3/2, right? This is n to the half, n squared. So you can rewrite it as 1 over n to the 3/2. That converges because it's a p series with p equal to 3/2, which is bigger than 1. So that converges. Okay, then S2, 4 times summation of 1 over n squared. I've got that on top here. Summation of 1 over n squared converges. That's also a p series with p equal to 2, which is greater than 1. Okay, so the two series converge. S1 converges, S2 converges, therefore the series converges, right? This converges to a number. This converges, which means to a number. A number plus a number is a number, so the series converges. Okay. All right, that was just about all I was going to show you, except for 19, and I'm noticing this is not the same 19, but it'll help us for next time when we do something called the comparison test. So this is a nice forerunner to that. Okay, so I'm almost done. So I'll be done in a few minutes. You can ask questions, and then if you don't have any questions, then we'll go straight to the quiz, and that's about it. I'll just mention some other things for the remaining problems on page 726. Right, and how far do we have to go up to again? Just up to 25. Okay, so I'll just make some notes about this. Let's see. 17, you can integrate that. So integral test, you probably want to compare it to 1 plus something squared, factor out the 4. So it's going to be an inverse tangent kind of game. This one should be an easy integration, right? The derivative of the bottom is almost the top. So that's going to be a U substitution. Same thing for this one, right? If you think of it as x, what's the derivative of ln x? 1 over x. Okay, so that works. So integral test pretty much works for these. And by the way, notice n equals 2. What's wrong with n equals 1? If n equals 1, you're taking ln of 1, which is 0. So that's why this index starts at 2. Okay, so I'll give you a hint for this one. Factor out the 4, the inverse tangent. This one looks like a direct substitution, right? The derivative of the bottom is the top almost. That's substitution. This one, a little bit harder. It looks like you have to integrate by parts. When you make it x e to the negative x. This one, make it n squared times 1 plus n. That's the hint I'll give you. And it looks like you might have to do partial fractions after that. Okay, so my hint for 25 is factor out the n squared, 1 plus n, which means you're going to change it to x squared, 1 plus x, and do the partial fractions game. Okay, so it's a little bit inconvenient for some of these, like 17 and 25 is actually going to be somewhat inconvenient. Okay, so I'm giving you an introduction to the next section, which is called the comparison test. I'm sneaking it in on you a little bit. Now, the last time I taught, there was summation of ln over n cubed. And I don't see that same problem here. Too bad. This is a good setup for the next section. Okay, now, I don't really want to do the integral test with this. I could. It'd have to be ln x, x to the negative third. So you would do the integration by parts. Instead, we're going to go like this. Okay, take a look at this. Here's y equals x. Here's y equals ln x. X is greater than ln x for all x, right? You can see x stays above natural log of x. X is greater than natural log of x, or just switching letters, n is greater than ln n. Okay, so I claim this. Ln n is less than n. That says the same thing as this, right? Just turn it around. Ln n is less than n. Divide both sides by n cubed. N is positive, so that still holds. And that's the same as 1 over n squared. Okay. What I'm really doing is I'm changing the problem. I think it'll converge. I'm going to find a bigger series which I know converges. So based on this logic, if you look at the graph, x is bigger than ln x, right? So I have ln n less than n divided by n cubed, 1 over n squared. Okay, so this thing is smaller than 1 over n squared. And what do I know about summation of 1 over n squared? That converges. It's a p series with p equal to 2, which is greater than 1. Okay. Therefore, by something called the comparison test, any series that's smaller than that also has to converge. That's going to be something called the comparison test, which I'll show you next time. Okay, so in other words, rather than integrating, which can be done, I change it to a bigger series which I know converges. Okay, so if this one converges, certainly anything smaller than that would also have to converge. I mean, this thing can't blow up. It can't go to infinity. How come? It stays below a series which I know converges. Right, so that's something called the comparison test, which I'll show you starting next time, because theoretically I'm done. Okay, and actually the comparison test works well with something like 25 also. And 17, the comparison test would work for that also. But we'll get that next time. 11.4, the comparison test. There's actually more than one comparison test. One of them is called the comparison test. Okay, but there's another comparison test just to whet your appetite, so to speak. The other one is called the limit comparison test. That's on page 729. Okay, as you might guess, I would like to abbreviate. So comparison test, page 727. Next time, I'll call it CT. And limit comparison test, I'm going to call it LCT. But I'll save that for next time. Okay, so I'm marking this off, so I'm good up to here. So 11.3. So next Tuesday, I'll probably aim for 11.4 and some of 11.5. Then Thursday, 11.5 and 11.6. So again, maybe a section and a half each day. I think I'll be able to land where I want to by the time the last test comes around. Okay. All right, so that's it. Let me stop the share. Check. I see nothing in the chat. Okay, so does anybody want to ask any questions? And if not, we'll go straight to the quiz and that'll do it for tonight. Okay, so any questions, please? Okay, I don't hear any. All right, so get your cameras ready. And so as usual, I'll give you the quiz. Then I'll put you in your breakout groups. You can leave whenever between now and 9:25. If your breakout group gets too few people, then be ready for me to move you here or there. Okay, so hopefully your cameras are ready. This is all section 1 stuff. So let's see. Get back to sharing your screen. Okay, so here we go. We're still recording, so worst comes to worst, this is on the recording. 1 and 2, just write the first 5 terms of the sequence. Pretty straightforward. Okay, so a sub n is -1 to the n plus 1 over 2n plus 1. And remember what happens to this, right? What happens when you raise -1 to certain powers? Okay, we said that makes the sequence alternating. Okay. Number 2 is a recursive definition. Right? They give you the first term, and then you get A2 based on A1, then you get A3 based on A2, and so on. And then 3 and 4 just ask whether the sequence converges or diverges. If it converges, what does it converge to? In other words, take the limit as n approaches infinity of 3 and 4. Okay, so number 1, just basically plug in 1, 2, 3, 4, and 5. Okay, a sub n is -1 to the n plus 1 over 2n minus 1. Number 2, the first term is 1, then a sub n plus 1 is 2a sub n plus 1. And 3 and 4, state whether the sequence converges or diverges. Limit as n approaches infinity. And by the way, state why. How do you know that's true? And likewise for 4. Okay, I'm assuming everybody got it now, so I'll stop the share and set up the breakout room. So go ahead and get started with it. But let me set up your breakout rooms. Possible. Okay, you should have an invitation to join your breakout room. So everybody join your breakout room now, please.